Hey, what's up guys? Welcome back to another machine learning video. In this video, I'm going to teach you guys how to do linear regression and multiple linear regression in more detail, now that we have an understanding of the basics of machine learning and how to pre-process our data sets. So previously, we built a simple linear regression model using scikit-learn, and that allows us to predict a simple best fit line for a very simple data set where you have one feature and one predicted value. But of course, in real life, datasets are not that simple. Usually you have datasets with many different features that have many different columns, and it gets way more complex than that. So what I'll be doing first is showing you guys how to do linear regression in more detail rather than just using a higher level library so that we can actually implement it ourselves using algorithms from scratch. So this video will include an implementation of the normally equation, which is an equation that can give you the result directly for the model parameters, but also gradient descent, which is a more complex topic that will be used not just with linear regression, but also other advanced machine learning things like even neural networks. So it's one of the hardest topics to understand, but also one of the most important in machine learning. So I'm going to try and give you guys the best explanation I can. So let's just jump right into it. This graph here gives a simple example of the type of data that we can model using simple linear regression. So we have on the x-axis the years of experience, and then on the y-axis we have the salary. So as the years of experience grows, so does the salary, and you can see that it's pretty linear, it's pretty proportional. So as it's growing, so does the salary. So what we can do is build a best fit line that can try and approximate the data in the best way possible. So you can see that it pretty much goes through the middle of all these points here, so that if you're given a years of experience, you can easily predict the salary by just going on the line, using the line equation to calculate that salary. And that's a very important thing that I should emphasize. The line itself is the actual model. So if you have a good model that can make good predictions, what that means is that you have the proper m or proper slope, you have the proper b or y-intercept, and then when you pass in a x, which is the years of experience, you should get a y that's pretty close to the actual value of that prediction. So a really good example here, if you have 6 years of experience, if you go up to that line, to that point, it should be about 80,000 in terms of salary. And this is only one data point as an example, but if that's a prediction you can get, this is probably a good model, assuming it does good for the other points as well, because you can see that the dot is directly on the line, but the other dots are actually pretty close as well. So it's not always going to be directly on the line. That doesn't make sense. You can't have a line that goes through all the different points. That would be an overfitting line because it only models those points and not, all the points in general that could exist. So anyways, this is the model itself, y is equal to mx plus b, which is a equation that you probably learned in middle school. So obviously in machine learning, you're not going to be using an equation like y is equal to mx plus b. In machine learning, you're going to have different mathematical representations. So let's take a look at how we can transform our basic line equation into a more commonly seen equation that you would see in machine learning. Alright, so for this first equation here, we have y is equal to mx plus b, and then that transforms into y is equal to w1 times x1 plus w2 times x2 plus all the way up until wn times xn plus b. So the y is going to be the same as before, that's just the predicted value of the model. B is also the same as before, this is going to be the y-intercept. But instead of calling it the y-intercept, now it's going to be known as the bias term, so that's what you would call it instead of the y-intercept. And then you have these different combinations of w1 times x1 and then all the way up until wn times xn. This is the corresponding terms for our slope times x. The only difference is that, of course, instead of m, we have w, and then x is still x, but now we have multiple of them, and this is because this equation allows for multiple features. So again, the feature in this case, for this very simple example here, would be our years of experience, and that gives you the actual value, which is the salary. But in a more complex data set, you could have many different things that determine someone's salary, such as their years of experience, maybe their age. I don't know if that would matter, but just as an example, their age, like any other factor that you would include into your data set. Those are the features that give you a prediction, right? So in machine learning, since we're going to need linear regression models that can do multiple features to make a prediction, this is why we have this. So n is the number of features. So for every single feature you have in your data set that you're making a model of, you have w, which is the feature weight, times x, which is the actual feature value, okay? So of course, we only have one feature for this simple example here, so the equation would be y is equal to w1 times x1 plus b. You just, not have any of these other ones here. But if you add another feature, you would just add on to that. So it'd be w1 times x1 plus w2 times x2 plus b. Again, w is the feature weight. So every single feature in our model has a weight associated with it, because different features in our model have different effects on the predicted value, of course, right? So anyways, with that said, that's another representation of the same equation here, but a little more complex and also allowing for multiple features. And then we have this equation here, which is probably one that you're going to see more often. So this is going to be y hat is equal to theta 0 or sub 0 plus theta sub 1 times x1 plus theta 2 times x2 plus all the way up until theta n times xn. So this one's even more different, but it's not too far off. So y hat, that's just what it's called, y hat with the little thing on top of it. This is the predicted value. So if you ever see y hat, that's the predicted value. But in machine learning, if you ever see y by itself, that's the actual value, okay? So for example, if you want to get the difference between the predicted value and the actual value, the equation would be y hat minus y, or the absolute value of that, okay? So what else has changed? Now instead of b, we have theta 0, okay? So this is theta with a subscript of 0, so this is the first parameter of our model. And so theta is now what we use to represent all of our model parameters, including not only the bias term as it says here, including the bias term theta 0, but also the feature weights theta 1, theta 2, and theta n, all the way up until theta n. So now, instead of using the term b for our bias term, we use theta 0, and then after that we add all of our feature weights and our feature values. So now, instead of w for each of these feature weights as well, it's using theta. So in our equation, like I said before, we only have one feature, so our equation for our model would be y hat is equal to theta 0 plus theta 1 times x1, and then you chop off the rest of it because we don't have any more features. And just like before, n is the number of features that you have, so that would be how far you go essentially. So however many n or however many features you have, the more combinations of theta and x that you would add to this equation that you have for your model. So hopefully this equation makes sense. I hope it's not too complex. I think breaking it down like I did up here and seeing how the equation transforms into this equation here is pretty helpful. Hopefully it's helpful to you guys. But one thing I want to point out is that we have y hat is equal to theta 0, but there's no x term here. So it's just theta 0 by itself plus all the features. But behind the scenes, you can actually imagine that there is an x here. It would be x sub 0. So it would be y hat is equal to theta 0 times x0 plus theta 1 times x1 and so on, right? The reason we don't have x0 here is because you just imagine it as 1. And that's a constant. So since the value of x0 is always going to be 1, there's no point in putting it there because that's always just going to be theta 0. So you'll see what I mean in the future. But basically when we start working with our models and training them, you're going to see that we're going to have a 1 at the very beginning, which represents the value that we multiply against the theta 0 for the bias term, okay? Okay, so there's one more representation of this same equation here that I want to show you that sometimes you'll see as well. So this is actually a function. This is called the hypothesis function, which just basically represents the model that you have. So it's a model that uses theta as the model parameters, and then x is the input to your model, okay? And that just breaks down to what we already have here. Another way of representing this is the dot product of theta and x, which literally, if you just break it down, is this as well. So it's literally just the weighted sum. That's also what it's called. The weighted sum, or the dot product, is literally just theta 0 times x0 plus theta 1 times x1 and so on. So that's how you represent it mathematically, okay, if you're actually doing the calculation itself. All right, so now that we have an understanding of how we represent the model mathematically, let's see how we can actually make predictions with that model. I want to give you guys a few examples here. So this is the equation that we'll use. And then at some point when you train your model, you're going to come up with a vector, which is theta, that has all of your model parameters. So the first one will be theta 0, which will be our bias term. And then everything after that will be our feature weights, which is theta 1, theta 2, and so on, okay? So this theta here would represent the model parameters for a simple linear regression model where it only has one feature. And we know that because since it only has two terms, you may think, oh, that's two features, but no, the first one is of course always going to be the bias term, and then everything after that will be the feature weights, okay? So with this theta here, we can plug that into our model equation, and that's how we can make predictions with our model, okay? So as an example here, our model is going to be y hat is equal to theta 0 plus theta 1 times x1, or y hat is equal to 0.65 plus 3 times x1, okay? So if you want to make predictions, let's just say our input is 2, right? So in that case, all we got to do is plug that into our model equation using our weights as well, and that will give us the result. So 0.65 plus 3 times 2, the 2 is the input, which is x1 in this case, and that's how we get the prediction of 6.65, okay? And then it's the same thing, so 4, 5, and so on. So that's how you can get the predictions of the model. Hopefully that makes sense. Again, y hat is the prediction. So here we are making very simple predictions, just one at a time, just plugging in these values one by one into this equation here. But of course, in machine learning, that's kind of inefficient. It would be nice if we can just calculate all of our predictions at once. And luckily we can do that using linear algebra. So what we can do is instead wrap everything in a matrix. So in this case, we have the matrix X is equal to, and then it's a 4 by 2 matrix, so we have 4 rows and 2 columns. So each of these values here is the actual input that we're passing into our model that we want to get predictions for, so 2, 4, 5, 7. And then we're adding ones because, like before, I told you we need something that will go with the theta 0 term or the bias term, because behind the scenes you can imagine a little invisible x 0, because there has to be something that you multiply this by. So you're just going to add a constant value of ones as the first column to your input matrix. And so once you have your input matrix, what this allows you to do is essentially have all of your input like combined together. And then what you could do is use a linear algebra matrix multiplication operation to actually get the prediction. So it would be y hat is equal to x times theta. So it would just be the multiplication of our input matrix times our model parameters vector. And with that, you should get a new vector, y hat is equal to all the predictions of your model. So the first one will obviously be the prediction for the first input in the input matrix. So 2 should be 6.65, 4 is 12.65, 15.65, 21.65, and so on. So that is how you can calculate predictions of input sort of all at once using linear algebra. And this is a representation that you're going to see more often. You're not going to be calculating it one by one most of the time, most likely. So that's how you can do that. And of course, it's going to be even more complex than this because in real life, you're going to have usually data sets that have more than one feature. And then if you do have more features, what you would do is add more columns to your input matrix. So this first one here is years of experience. So if you have age, you would just add another column and add the values for that. And then for this calculation here, you would still have your input matrix, but the model parameters vector would have to have another term that represents the weight, the feature weight for the feature that you just added. So it would literally be the same operation is what I'm trying to say. You just have to change the input matrix in the model vector. Okay, so hopefully you're all with me so far. Hopefully that's all making sense. I'm trying to explain this best way I can. So now what we're going to do is actually jump into how to actually find the theta or the model parameters for our machine learning models, or more specifically our linear regression models. Because as you just saw, as long as you have theta, which represents the model weights, you can actually make predictions really easily. So the normal equation is one way to get the best weights for the model. It actually provides them directly without having to do any complex algorithms. It's known as a closed form solution, meaning that it gives a direct solution that minimizes the cost function. I'll talk more about the cost function in just a second here, but basically it's just a way of determining how far off the predicted answers are from the actual answers of your model and your data set, okay? So that's pretty awesome, right? If it gives the answer directly, the weights that we need for our model, then we don't have to do a lot of work. You simply just use this formula here and you got the answer. But of course, there's other algorithms and ways to get the proper model parameters for a reason. And the reason is because this is useful for situations where your dataset is smaller rather than larger. As the dataset gets larger, the time it takes to calculate this equation to get the model parameters grows in time complexity. So a dataset that has maybe 30 features and 10,000 instances differs a lot from a dataset that has 300 features and maybe hundreds of thousands of instances or like actual data points in it. Now, I think the data sets that you're going to be exposed to as a hobbyist for machine learning are going to be much smaller compared to something that a commercial application is going to be using for their purposes. So I'm assuming that this equation should be good for most purposes that you're going to be exposed to. But there are other techniques such as gradient descent, which we're about to talk about, that I think you should still know because not only will it be important for more complex data sets for linear regression, but it'll be useful for other things like neural networks, which we're going to learn about in the future as well. So either way, you still need to know it. So I'm going to show you guys how to do it. And it's a huge part of machine learning in general. So yeah, so again, the normal equation gives you the answer directly, which is really cool, but as the size of our data set grows in complexity, so does our time complexity to calculate the answer for this equation, okay? So that's why we're going to talk about gradient descent now. Before we do that, though, I'm going to give you guys a little bit of a refresher on the calculus involved in this, because I don't know about you guys, but I did graduate from college, and we did have to take calculus and linear algebra and all those things, but if you don't put it into practice all the time, you're not constantly using it, it's easy to forget a lot of these concepts. So gradient descent was pretty hard for me to figure out. Like, I could not find a book or a video that explains it in a way where I understand it. But once I went back and actually tried to understand some of the calculus behind it, it made a lot more sense. It instantly became more clear to me. So what I'm going to be doing is giving you guys a little bit of a refresher on calculus so that hopefully you can also have that same experience. It will make more sense to you more easily, okay? So first is the concept of a derivative, which you may have heard of before. The derivative is a way of getting the slope of a curve at a certain point. Or another way of thinking of it is the derivative tells you how a function f of x changes as x changes. So just if you imagine this function here, f of x is equal to x squared, this is what it looks like when it's plotted. You've probably seen this before. And then you can find the derivative of this function, so d over dx of x squared is equal to 2x, just using the laws of math for determining a derivative. or you could just throw that into a calculator to make it easier for you. So that's 2x, and if you plot 2x, this is the line that you get. This isn't too useful here, but basically what this equation gives you is a whole other function that represents the derivative of this function here. But using this, you can then get the slope wherever you are. So for example, if I'm a point on this plot here, x squared, and I am at -2 right now, x is equal to -2, I can determine my slope just by using the derivative. So 2 times -2 is -4. And that kind of makes sense because we're heading in the negative direction. We're going downwards. So that's why we have a -4 slope. And again, if you don't remember, the slope of a line is the measure of the steepness in the direction of the line. So if my slope is -4, that means I'm going down, and that's different from like -2. So if I have a slope of -4 versus -2, -4 is obviously more steep. So that's what that magnitude represents, and then the negative simply means you're going in the downward direction. Okay, if I change my x to 0 and I want to get the slope at 0, that'd be 0 times 2, so that would be 0. So I have no slope in this point here. And then 2 would be 4, so +4, so I'm going upwards. But anyways, this is a cool little graphic of what that kind of looks like. So it's a little blurry, but if you look closely, you can see that as I'm moving through this curve here, I'm plugging the current x value into this derivative function. So that's what the f with the apostrophe is. It's the derivative function. So you're passing your x into that derivative function, and you're getting the current slope. So this line here, as you can see, as it's moving, is representing that slope line, okay? So obviously, depending on where you are, you can have different slope. So that's why you can see it moving differently depending on where you are. And yeah, that's literally all a derivative is. It's a way of getting the slope at a point. But I think just if you had to sum it to one sentence, the derivative of a function tells you how that function changes as x changes, okay? Which is really big when it comes to what we're about to learn, all right? But once you know derivatives, you also need to know partial derivatives, all right? So a partial derivative is useful when you have a function with multiple variables within it. So if we have a function that has variables not just x, but also y, and maybe others, we can determine how that function changes when those particular variables change. So let me give an example here. So we have this function with x and y, 5x minus 2.4y squared. And now this is a more complex function because it has multiple variables. So now it's multi-dimensional. All right, so if you look at the bottom here, the partial derivative gives how a function changes with respect to a specific variable while the other remains constant. So what that means is that if I find the partial derivative of this function with respect to x, that means that I can figure out how this function changes when x changes by a little bit, but the other variables stay the same. And then correspondingly, if I get the partial derivative of this function with respect to y, what this allows me to do is see how the function changes if I change y, but leave the other variables constant as well. So all this symbol means here is that you're finding the derivative, d over dx. X is specifying which variable you're finding it for. So this gives you 5, so it's pretty much just a constant. But this one's a little more complex. So if you find the derivative of this function with respect to y, d over dy, you get -4.8y. Anyway, so now we can move on to gradient descent, now that we understand that a little bit better. So when you're doing linear regression models, we can measure the accuracy of the model using different formulas, different equations, one of which is the MSE, or the mean squared error, okay? I'll go into more specifics in the future on what these functions mean in a little more detail, but for now, it generally just tells you how far off the predicted values of your model are from the actual values of the dataset. So whenever you have a model, you can calculate the mean squared error, which again tells you how far off your model is from the actual values of the model, or what the model should be, okay? So the mean squared error is very commonly used with gradient descent and linear regression, so that's what we're going to focus on in this particular example here. So anyways, when you are training your model by choosing the weights for it, you can calculate the error or the cost by using this formula, right? So this little plot here actually visualizes that a little bit better for you. So on the x, we have theta, which is our model parameters, as you know, so the bias term and also the feature weights that we're going to choose for our model. And then on the y-axis, you have the cost, or the mean squared error, okay? And I think this intuitively makes sense, right? So as you have different thetas, you have different costs, because some thetas are better than other thetas. So you can imagine initially when you start training your model for the first time, that you're just gonna have some initial theta for your model, and then the cost can be up here. Because unless you make a really good guess, your initial cost or error is not going to be very good because you just started training, right? So the whole idea behind training a model is that you get a better and better theta, so you should descend down this error plot that we have. So initially, it's going to be high, but if you're doing things right, you should get better and better thetas, and therefore lower and lower costs. So you're descending down this curve that we have. And then eventually you're going to reach a minimum, a global minimum, hopefully, which is the very lowest point of the entire graph. And if you understand what I just said, that's the whole idea behind gradient descent. You're trying to descend down the cost function with regard to your theta. Now the question is, how do you actually do that, right? How do you actually descend? So I'm going to give you the actual steps in just a second here, but this is where partial derivatives come in. If we can calculate the partial derivative of our error function with regard to every single variable in our theta vector, we can figure out how the different parameters of our model affect the function in different ways. Because as you can see here, we're calculating the partial derivative of MSE with regard to only theta 0, and then this one's doing the partial derivative of MSE with regard to theta 1. Which, like I said before, allows you to see how, for example, the bias term affects our cost, as well as the feature weight theta 1 affects our cost, okay? And the reason we have to do this is because if theta is going to have all of the model parameters within it, such as our bias term and all the feature weights, increasing the bias term by whatever number may make the cost go down, and that would be theta 0. But if you increase theta 1, that may make the cost go up. So the individual different variables of your theta are going to have different effects on the cost. So that's why we want to get those partial derivatives, because we can then figure out which ways we need to tweak those values to get the optimal cost, or get the cost to go down rather, until we reach that global minimum that we talked about at the very bottom here. So let's talk more about the specific steps of how to do gradient descent, and we're actually going to be implementing this algorithm from scratch. So don't worry if you don't fully understand it now, but I just want you to have a high level understanding at least. Theta is all we care about, right, to actually build our model, because like we learned before, theta is all we need to actually make predictions. We just throw that into our formula and boom, we can make predictions. So we're going to take theta as a vector and just give it random values. It doesn't matter what the values are, just give them random values, and then we can immediately see where we are in this little imaginary function here. We can see what the cost is, and then we can try and minimize the cost throughout this algorithm, okay? So once you have those random values for the theta, you can calculate the gradient of the cost function at the current point. And all this means is that you want to calculate the current slope based on where you're currently at. And to do that, all we have to do is use our partial derivatives that we already have, right? So using these functions that we have, we can figure out the slope, or otherwise known as the gradient, which is a representation of which direction we are heading, essentially. So what we want to do is move in the opposite direction. So what we want to do is essentially move in the opposite direction, because if you can imagine, if the slope is positive, and that means that you're going up the curve, so that means that we want to subtract by that value. So what we want to do is take the current model parameter. So let's just focus on one of them, right? Let's just focus on like theta 1, for example, right? We're going to initialize theta 1 as a value. We're going to calculate the gradient of the cost function with respect to theta 1 to figure out which way we're going, essentially, in terms of the slope. So then we're going to use our partial derivative to go in the direction that leads us downward. So whether that means we need to increase theta 1 or decrease theta 1, whatever gives us a lower cost, we want to go in that direction, okay? And we're going to use that using the partial derivative. So that's all I mean by moving in the opposite direction of the partial derivative to travel down the curve. You're just going to go in whatever direction decreases cost, so it makes you go down the slope to find a global minimum. So you just want to repeat that process until you find that global minimum or the iterations run out. So what you can do is have this run forever until it reaches a global minimum, or more realistically, you're going to set a limit, a max limit on the number of iterations that this algorithm runs in, because running forever doesn't make a lot of sense, because you can keep moving really slowly, and that could go for a long time. So maybe you set like 100,000 iterations, or 10,000 or 1,000. It depends on how you want to tweak your model, okay? So I really hope this makes sense. Just as a high level, we're choosing a random value for our theta vector, so random model parameters, and then we're going to iteratively, meaning in a looping way, we're going to over and over calculate which direction we need to go to travel down the cost function with respect to our individual theta variables, so that we can not only have the best model parameters but the lowest costs, okay? So that's the whole idea behind gradient descent, and we're going to implement that in just a moment here, okay? Whenever you're dealing with training machine learning models, you have these things called hyperparameters, which are not the model parameters. The model parameters is like your bias term and your weights and stuff like that, but the hyperparameters is what you're going to use to actually configure how it's trained. So one of them is the learning rate. So when we're going through this process of descending down the cost function to find the optimal cost and optimal theta values, we're going to multiply our gradient times a learning rate, which is a value that basically allows you to customize how far you're going to step based on that gradient value. So let's just say that if our slope or gradient is 5, we can multiply that value times a learning rate value of like 0.01, for example, and the result of that operation chooses how far we're going to move. So for the first example here, if we have a learning rate that is too low, this means that it requires many updates before reaching the minimum point. Or maybe it never reaches that point. You run out of iterations and you never reach the global minimum that you want to reach, right? So you can see that it's moving very slowly. You can also have a learning rate that's too high. So it says too large of a learning rate causes drastic updates which lead to divergent behaviors. So as you can see here, if we have our learning rate too high, we can really jump around this cost curve that we have in a way that's not what we want, because we can totally bypass, as you can see here, the minimum. So we're here, we're bypassing the minimum, we never even reach it, and then we jump back up. So obviously a learning rate that's too high, you're stepping too far, is not optimal. So you want a learning rate that is just right, and you're going to find that just right learning rate by tweaking your model continually to see which one is best. So the optimal learning rate swiftly reaches the minimum point. So swiftly is key here. We can have a low learning rate that just takes forever to reach that point, or you can have a learning rate that's higher but not too high so that it reaches that minimum point in a faster amount of time, but also in a way where it doesn't skip over the global minimum that we need to reach, okay? So the learning rate is a very important piece of this gradient descent algorithm that we need to make sure that we tweak properly, okay? And we're going to see how different learning rates and different hyperparameters affect our machine learning model training process, okay? So that is all for the presentation here. Hopefully you guys understand a little bit about what we're doing here for multiple linear regression and just linear regression in general with gradient descent. With this, now you guys should have a high level understanding of what linear regression is, what a model is. All we have is these theta values, this vector of theta values that we're going to plug into a formula, and then we plug in our actual x values into that and get a prediction from that. But then besides that, we learned about two different ways we can come up with those proper theta values. You can either use the normal equation or you can use gradient descent. There's other ones out there, but those are two of the most popular ones, okay? So with that said, guys, I hope you understood all of this. If you have any questions, just let me know in the comment section below so I can continually improve my tutorials. And now let's move on to the fun part, which is actually jumping into our code and implementing each of these algorithms in different ways, okay? Let's start by implementing the normal equation. So I'm going to create a new notebook for that purpose. So the way this will go is we're going to create a notebook for the normal equation to demonstrate that. We're going to create another notebook for the gradient descent algorithm. We're going to implement that from scratch for just a simple single feature data set. And then we're going to implement another notebook for multiple linear regression, meaning that we have multiple features in our data set that we want to model with linear regression. I think with all of this, you'll get enough practice to really understand how linear regression works, okay? Pandas, import pandas as PD. Import NumPy as NP. And here's a fake dataset that I want to use to actually practice this. This is the years of experience and salary dataset that we made that graph on originally in the presentation. So what we're going to do is download this. It's going to give us a zip file which we want to open, and it's just going to give us a CSV file that we can upload into our notebook and reference. Looks like it didn't work because make sure that you extract this into something that's not a zip file because it won't let you upload it otherwise. So now I've got it into a regular folder, so I'm just going to drag and drop it. There we go. So now it's uploaded. So now we can reference it, or we can actually view the data by clicking on it as well. So we can start by just loading it into a data frame. We already know how to do that. So df data frame is equal to pd from pandas read csv. And then now we need to specify where that's located. So we can do, should just be in the same directory. So salary underscore dataset dot csv. And let's just go ahead and print out the head of our data frame just to make sure that this worked. And here it is. So now we have our data frame. It looks like we have an index column. So this just has the index of each of the samples that we have or instances. We don't need that, so we can remove it by doing something like df is equal to dataframe.iloc. We want all rows, but then we want to essentially cut out everything after the first column. So 1 and then colon, and that should do it. So that's just going to take everything after the first column and put it into a new data frame. So replace the original data frame. So if we rerun this, that looks a lot better. What we can actually do is plot the data so we can get a better look at what it looks like. So we can do import matplotlib.pyplot as plt. And then now that we have all that, we can do plt show, and that will show the plot. So we can run this now, and boom, now we have an idea of what our data looks like. So we just need to figure out how to make a linear regression model or line that goes through this. All right, so remember the normal equation is just a closed form solution for linear regression, meaning that it gives you the parameter vector directly, just using this formula here. So theta is equal to x transpose times x, and then the inverse of that times x transpose times the vector y. So to do this actual calculation here, we need a matrix X and then Y. So we can do X is equal to data frame, years, experience, dot values, which will give it to you as a NumPy array, as well as Y is equal to data frame, salary, dot values as a NumPy array. So let's just print that out to see what it looks like. So now we just have a simple NumPy vector, so a single dimensional array essentially, which has all the values of our years of experience column. But usually we want this as a matrix, right? Especially for this formula here, this capital X implies that it's a matrix. So to get this as a matrix, you can actually just reshape it. So X is equal to X dot reshape. And then we could do -1 and 1. And then we need to print out X again. And boom, there we go. So now we can see that it's a multi-dimensional NumPy array, which is a matrix. And it's just a matrix with one column, which is the feature of our data set. What we're going to do is make a function for this formula here. So we can do def normal equation. We could say it takes as input the x and the y, and the implementation is going to be return np, so numpy dot linear algebra, so linalg dot inverse. So inv stands for inverse, is the inverse function. The reason we're doing that is because we want the inverse of x transpose times x. So we can do that now inside of here. So x dot t for the transpose of x dot, and then we can do x like that. So now we're doing x transpose times x, getting the inverse of that. And now we want to multiply that times x transpose again. So we can do the dot of x dot t. And then finally we multiply times the vector y. So we can add another one, another dot y, just like that. And now we can call this function too if we want to. We could say theta is equal to normal equation. And we pass in our x and our y that we already got above. And then we could just print out theta. So let's try this out, see if it works. And boom, it gives us this single value here inside this vector. But you may notice here that something is off. We should have two values, right? So our parameter vector theta should have two values. It should have the bias term, theta 0, and then the actual feature weight, which is theta 1. In this case, we only have 1, so that's incorrect. And the reason for that is because the feature matrix X should have a column of 1s that you can use to multiply against the bias term. Because when we specify the weighted sum formula, y hat is equal to theta sub 0 plus theta sub 1 times x1 and so on, we don't write out usually x sub 0, that's implied as 1. So it's not there in the equation, but we need to actually have it in the data set, because if we don't have it there, there's nothing to multiply it by. So all we got to do to fix that is just go here and do x is equal to add underscore dummy underscore feature. That is a function from scikit-learn that we can import. So we can do from sklearn dot pre-processing import add dummy feature, just like that. And then now we can reference it down here, so we can just pass an x, and now what that will do is add to the first column of our matrix here just a bunch of ones. So it's a column of ones, which will be for the bias term of our parameter vector. So if I rerun this, look, now we get a matrix same as before, but now we get ones, but then we also get the values of the feature as well. Okay, so now when we run our normal equation again, now we get two values. So we get 24,848 and also 9,449. This is a vector representing our theta, or our parameters for our model. The first one's going to be theta sub 0, and the second one's going to be theta sub 1 for the feature. And now that we have these model parameters, we can test it out. We can actually get the predictions. So predictions is equal to, we can do x dot theta. So this will just take our input matrix and multiply it times theta, which is our model parameters, and give us the actual predicted values, because that's the weighted sum. So if we print this out, predictions. And this doesn't really mean much. These are just numbers, and it's hard to sort of see if these have any relevance or if they're correct at all. So one way we can, make sure it's correct is actually just by visualizing it. We could do that by plotting it on another graph. So if we plot it, so now we have our same plot as before with all the blue dots, but now we also have our red line, which is created by taking all of the predictions of our model. I don't know about you guys, but I think that's pretty damn cool. So we have created our very first linear regression model from scratch using the normal equation, literally one line of code. Here's another piece of code that probably helps a little bit. So we have a data frame we're displaying in two columns. We have the actual values of our model, as well as the predicted values of our model. So we're providing y, which you already got above, but we also got our predictions as well. So, and again, the normal equation is good when you have a relatively smaller data set compared to something that's like 300 features or maybe even larger with hundreds of thousands of actual samples. So for a situation where you have a larger data set, you may want to use a technique such as gradient descent. All right, so now let's jump into implementing gradient descent for a simple linear regression model. Then we'll jump into doing the same thing for multiple linear regression for a model with multiple features. It's going to be the same for the very beginning, same as we did with the normal equation. We're going to import our data set, print out the head. This is what it looks like. We're going to plot it, same as before. This is what our data looks like, just so we can visualize it. And then I copied in this little description here. So linear regression with gradient descent. It's an optimization algorithm used to minimize some function by iteratively moving in the direction of the steepest descent as defined by the negative of the gradient. So the steps of this algorithm will be initialize the parameter vector theta with random values. So those are our model parameters that we're trying to find the best values for. And then we're going to calculate the gradient of the cost function at the current point with respect to those different parameters. And then we're going to change those model parameters by moving in the opposite direction of the negative gradient to minimize the cost function. So what that means is that if, for example, we calculate the partial derivative of our cost function with respect to a particular theta value, and it's going up, we want to go the opposite direction down. So that's all that means. We just want to change our vector values in a way that makes our cost go down, okay? And then we're just going to repeat those steps 2 and 3 until we run out of iterations, okay? So the function that we seek to minimize is the mean squared error function that we talked about before. This measures the average of the squares of the errors or deviations, that is, the difference between the estimator and what is estimated. So at a high level, all this means is that we're able to gauge how far off our predicted values are from our actual values. So that's an overview of the steps we need to take along with the cost function that we're trying to minimize. So now we just need to do the same thing as before. We're going to extract our features into this X matrix. So we're going to reshape it to be a matrix. And then we're going to have our Y, which is our actual values, as a vector. And then we're going to add a dummy feature, which is just a column of ones at the very beginning. And we're doing this because we have our bias term, which is the first term, theta 0, and we just need that column of ones to serve as a constant, essentially. So that's going to print out X. Here's our X matrix. And so now once we have that, we can then set up our hyperparameters for our models. So gradient descent usually is going to have at least 2 hyperparameters, sometimes more. And what we have, first of all, is the alpha. That's going to be, we'll set it to 0.01, which is also known as our learning rate. This allows us to control how much we want to step whenever we're moving down the gradient. The lower this value is, the lower we're going to step. The higher this value is, the more we're going to step, if that makes sense, okay? So that's our alpha, our learning rate, and then we also have epochs, which is basically the number of iterations. So we can set it to 1,000 by default. So this will be the number of iterations that we do when trying to do gradient descent. So that means that we're going to step 1,000 times, okay? So that might be too small, that might be too high, or we just have to find out by running this algorithm and seeing what it gives us. And then now the first step of this algorithm is to initialize the parameter vector theta with random values. These are our model parameters, so initialize model params with random values, because it doesn't matter what the values are to begin with as long as we are able to descend down that gradient. So theta is equal to numpy.random.rand in2, and all this will do is give you a vector with 2 values within it that are random, so we can print out theta, and boom. So this is our theta. We have 0.54 and then 1.42. Doesn't matter what they are as long as they exist, and then we could tweak them, right? All right, so the next thing is the partial derivatives, right? So we have our cost function, but we need to figure out how each of these values within our theta affect that cost function, right, wherever we are. So calculating the partial derivative of our cost function with regard to these individual values of theta will give us these formulas that we can use to calculate that gradient at any point. So this is the partial derivative of MSE with regard to theta 0. Here it is. And then this is the partial derivative of MSE with regard to the feature weight. So that's how you can get the partial derivatives for MSE for our different model parameters. This is for specific instances. That's why we have X, I, and YI. So that's a specific instance from our data set to find the MSE for, but we're going to sort of generalize this so that it applies it over our entire data set, meaning that we can get the MSE for every single instance in our data set all at once and sort of get a single value for that to figure out how good our model is. And then we can use that to also figure out which way we need to adjust our weights, okay? I think this will actually become more clear as we implement it, so let's get started on that. So we're going to just define a new function called gradient descent, like that. We're going to pass in our X input matrix, our Y actual values. Then we'll do theta, which is our model parameters. We're going to do alpha, which is our hyperparameter for the learning rate, and then epochs, which is our hyperparameter for the number of iterations for gradient descent. Oops, this is Python, so we're going to do that. We're going to create a for loop here, so for in range epochs, so this will loop for the number of times that you specify for epochs. And then for each iteration of the loop, we want to basically follow this template here. So we already have initialized the parameters of theta. Now we want to calculate the gradient of the cost function at the current point. So we're going to start by doing theta 0 partial is equal to, and then now we can just simply use this formula here, but instead of for a single instance, we're going to do it for all instances. So just try and follow along. So first we're going to do 2 over m. We haven't defined m, we'll do that in a second. So 2 over m times, and then now we want to sum. So to do a sum in NumPy, we can do np.sum, and then whatever you pass in here will be summed. So the thing that we want to sum now is going to be basically all of our predictions subtracted by the actual values, okay? So to get all of our predictions, so we can do predictions, and the calculation that we want to do is the one that I'm showing on the screen right now. This is what we saw before, which is our weighted sum. So we're using our theta, plugging that into our model function essentially, and then getting our predictions from that. So we're going to do x dot theta. And we're able to do dot on x because this is a NumPy array representing a matrix. So now what this should be is a vector with all of the predictions for every single instance in our data set. So for every single row of x, now we should have a prediction because we're multiplying that against theta, right? So with that, we can complete this theta partial that we have here, this function. This one is our predicted values. So we'll do predictions. And as the formula says, we want to subtract that minus our actual values, which is just going to be y, just like that. And there we go, that's the partial derivative of MSE with regard to theta 0. Now we can do the same thing for theta 1, so it should be almost the exact same thing. Let's just copy it. So theta 1 partial is equal to the same thing, but the only difference is that we're going to multiply it times x again. So to do that, we're just going to do dot x. I really hope I'm explaining this well enough for you guys. I think it's kind of cool though how you can have these formulas here and then directly put them into code really easily using NumPy, just using these built-in functions that we have access to. Ooh, I'm a ghost. This is me from the future. So I made an error when I wrote this out. So we did this part correctly, but when we do the dot x like this, we want to do it inside of here and then surround this part in parentheses. So we're calculating the difference between the predictions and the actual, and then we want to multiply that times x. And then we want to sum it. And that's because I looked at this incorrectly before. The x is inside of the summation, not like outside of it. So you can't sum and then multiply it times x. You need to get the difference and then multiply it times x, and then sum it, and then multiply it times 2 over m, okay? So just make sure that you write it like this before you continue. Okay, so now that we've done these calculations here using our partial derivatives, this is going to give us basically the gradient with respect to each of our theta parameters. So now we know the slope, the direction in which our error function is moving based on that theta that we have. So now what we're going to do is update the weights with the gradients. So we want to do it for each of our theta parameters individually because we have these individual gradients that we've calculated here using the partial. So we can do theta 0 to access a specific parameter from our theta vector is equal to theta 0 minus theta 0 partial. But we don't want to just subtract it directly. We want to multiply that times our alpha, our learning rate, so that we can only step a certain amount. And we'll do the same exact thing for theta 1. So we're changing our feature weight here, theta 1, depending on our gradient that we've calculated and moving only as far as our learning rate lets us move. Guys, I'm editing the video right now and I have discovered something absolutely horrific. Whenever I update our theta based on the partial derivative that we've calculated, I updated the first one correctly using the alpha and the theta 0 partial, but for the second one, theta 1 is equal to theta 1 minus alpha times. You can see here that I clearly used the original one. I didn't update it to theta 1 partial. So I'm going to leave this in the video because it still shows you how to code gradient descent. But yeah, that's an unfortunate mistake. So hopefully you caught that as I was doing it. So even though I kind of messed this up, and we get decent results either way, but even though I kind of messed this up, you will see in a second that we're going to learn a better way where you don't have to update each of the thetas one by one like this. This is not a very efficient way of doing it anyway. So in a second, I'll show you guys how you can update all of your thetas all at once instead of how we're doing it here, okay? So kind of an unfortunate mistake, but yeah, good thing I caught it. And one thing we need to do is actually define m. M is going to be the number of instances that we have in our data set. So let's do that above. So we're going to do m is equal to the length of y. That's just the number of instances that we have. And that's it. That's all we're going to be doing for every single epoch of gradient descent. We're going to basically calculate our predictions, figure out the gradients using the partial derivatives of the MSE cost function, and then update our weights by a little bit using our learning rate and that gradient, our partial. And then finally, what we want to do is return theta once you're done looping, because theta now, if this worked correctly, after all the epochs, theta should have the optimal theta values, or pretty damn close to it. Okay, so let's go ahead and test this out. So we're going to do theta is equal to gradient descent. We want to pass in our x, pass in our y, pass in our theta that we've already set above right here, and then also pass in our alpha and epochs as well. So alpha epochs, just like that. And boom, look at that. It just spit out two values for our bias term and our feature weight. So theta 0 and theta 1. And we really have no way to know if this is correct or not until we test it out. I'm going to show you guys a basic way of determining if this is correct or not, and then in the future episodes, I'll show you guys more metrics that you can use to see if your models are accurate or not using different stuff like MSE and others, okay? But before we continue, just take a deep breath because that's literally it for gradient descent. This is a gradient descent algorithm. It's so tiny because, of course, like Python makes it easy to do a lot of things, but the hard part was just, in my opinion, understanding how it works. Once you understand how it works, actually implementing it is so easy. Just as a recap, again, we are initializing theta to random values. We define our alpha, our learning rate, and our epochs, the number of iterations that we're going to do. And then we call our gradient descent algorithm, which is going to, for however many iterations we set, we're going to get our predictions, and then we're going to calculate our gradients by using the partial derivatives of our MSE with respect to our theta. And then once we have those gradients, we know how to update our weights. We're just going to subtract them by that gradient multiplied times the learning rate, so we move only a tiny little bit, hopefully not too much, not too little. And then once we have done that however many times, we can then return our theta, which is our vector that we had before, but now instead of random values, we should have values that hopefully can represent a good model, okay? These are the weights of our model, essentially. Now with the proper theta vector, we can now make predictions using, anything that we want to. Let's just start by getting the predictions of the x matrix that we already have. So x dot theta, just to multiply x and theta together to get the predictions vector. Let's print that out. And boom, there's all the predictions. So of course, that doesn't really mean much to us. So let's go ahead and plot it. You can plot this pretty easily. I'm just going to copy and paste it though. And here we go. So here's the plot. So we have our data points, same as before, but now we have graphed our model simply using the theta values that we have calculated. I would say that's a pretty good model. What I want to do now is show you guys how you can modify this function here for gradient descent to store the error at every single epoch so that we can see how the error decreases over time. So when we start the function, we're going to create a new empty array. So errors is equal to that. And then every time we make our predictions, we're also going to calculate the mean squared error directly instead of using the partial derivative because we want the actual value of the mean squared error. So we can do error is equal to, and then we have the formula up here. So I'll just copy that essentially. So I'll do 1 divided by m times the sum of the difference between the predictions and the actual. And then we also want to do that to the power of 2, which we can do with that. So that will square it. And then once we have this mean squared error, we can append it to our array that we have. So errors.append and then error. And then at the very end of the function, when we return the theta, let's also return the errors. So this now returns a tuple, which is just how you can return multiple things from a function at the same time. So then we could grab the errors from it now. And so now not only can we print out our theta, but we can also go down here and print out a graph that represents how the error changes over time. And we could also print out the final error, so the last value in this array. So errors -1, which will get the last element of the array. And boom, so here's the last element. That's a really high error. That's probably not very good. But what's cool here is that, as you can see, as the number of epochs increases, each element in the array is represented by a single epoch, right? You can see that the error goes down really rapidly. But you can see that it goes up to 1e9, which is the exponent essentially. So that's why it's so large. So this isn't approaching 0. It's approaching like a really, really big number, which happens to be this here. But as you can see, it stops going down at a certain point. So that's a good sign. So that means that we've probably reached the minimum of our error function. The issue is that it's happening very quickly, but it doesn't sort of go down beyond this very large amount. So we've reached a minimum, but we don't really know why it's still so high. And one of the reasons that we're getting such a weird result here is because we're building a model for a dataset that only has 30 instances. It's very small, so that's one of the main reasons. But I have verified the results of this, and it does seem to be correct, close to the result of what someone else got. And also you can see that the line is pretty close. Obviously you can probably tweak it a bit, and that just means that you just need to tweak your hyperparameters, because as long as you code the gradient descent function correctly, the algorithm, that should not be something you have to change. The implementation should always be the same. So what we could do is experiment with changing some of these hyperparameters that we have here. So the number of epochs is the number of times that it iterates, right? As we can see though, the number of epochs doesn't really have an effect on the learning of our model, because it immediately plateaus at the very beginning and doesn't decrease from there. So increasing it from 1,000 to 100,000 would not really change anything. So what we could do is play around with the alpha, our learning rate, to see if that has any effect at all. So let's just try setting it to a really low value and see what that does. And then we can experiment with a higher value, okay? So we'll run this again, run this one again, run this one, run this one. You can see that the line is way off now, so obviously something went wrong. It's not able to learn correctly. And let's scroll down again, and so this one makes a lot more sense, right? Because you can clearly see that over time the error is shrinking. We still have a very large number, and hopefully this all makes sense to you guys. It does to me. So the reason that our line here is so inaccurate is because obviously we have not given it enough time to learn. So since we've shrunken the learning rate, it needs more time to move down the descent, right? So we left the iterations on 1,000, and so 1,000 clearly is not enough. So let's increase it to maybe 2,000 and see if that has any effect on it. There we go. We can see a much better line now. That's a great sign. Okay, and here we go. So as you can see, we have increased our iterations to 2,000, and it starts to slowly plateau down to a limit where it does not decrease much anymore. So let's go ahead and bump it up to 10,000 and see what kind of results we get. So that should be a much better value for that. Look at that, still a pretty good line. Boom. And look at that, now we have a clear representation that our model has learned as much as it can. So we've set the learning rate to a really low amount, which makes it slower at learning, but now we've set the number of iterations to a higher amount, so it's able to still take enough time to use that learning rate to learn. So you can see that it decreases within about 2,000 iterations, reaches a plateau, and then it doesn't really move much from there. So even though we're not getting a very good error, we can see that the line does fit pretty well, decently well at least. I'm sure with a better data set, it would learn better. But also what's really important here is that you just need to understand how the hyperparameters have an effect on how the model performs and learns. So that's really cool to look at. So just as one more example, let's set it to a higher number. Let's just say, I think it was 0.01 initially. So let's do 0.1 with still 10,000 iterations. Or let's do 1,000 just to reset it back to the default so we can see what that does. Let's take a look. So you can see that the line hasn't really changed much. So it looks like it's still able to learn. Okay, so here it jumps down really quickly, like very rapidly, so that's a little concerning to be honest with you. So basically it reached that plateau way faster than it did before because the learning rate is higher. But again, the issue is that it doesn't really go down from there. It's still a really high amount. So as you can imagine, the number of iterations or epoch does not really matter as much for this particular learning rate because it's able to get to where it needs to go much faster. Hopefully you guys understood all of that. That's how you can implement gradient descent for simple linear regression. Besides the actual error value for the mean squared error being so high, I think this is a great example of how you can implement this algorithm because we have now built a model that can serve as a best fit line for our data set, and we coded it from scratch, just using our understanding of derivatives and partial derivatives and the basic gradient descent algorithm concepts. So really cool stuff. What I want to show you guys now is how to implement gradient descent in a little bit of a more efficient way so that it also supports multi-dimensional datasets, or in other words, datasets that have multiple features. Okie dokie, so this is gradient descent with multiple linear regression. The main difference between what we just did and this one is that, of course, the dataset is different. We have a dataset with multiple features. That's why it's called multiple linear regression. Since our dataset is more complex with multiple features, it doesn't make sense to calculate the gradients using the partial derivative one by one like this. So you would have to each time modify your gradient descent algorithm to support each of the features that you add, depending on how many there are. And you could potentially have a dataset with 300 features that you're trying to train a model on. So doing that would kind of suck really bad. So to make this better is what we can do is calculate the gradient of the cost function with respect to all the weights, and what we can do is get a vectorized implementation of the gradient as follows. So this little formula here gives you the gradient as a vector for every single parameter of our theta. So the output of this is not a number anymore, it's going to be a vector. That way we are not calculating the partial derivative one by one, we are just having the result all directly in one single vector. And so the first one obviously will be the gradients with respect to the bias term, and then the first feature, and then the second feature, and so on, okay? And as you can see, the equation is not too difficult to understand. It's actually, in my opinion, simpler than the one we just did previously. So a lot of this will stay the same. What's different is we're going to need a different data set, obviously. So what I'm going to do is import something called the California Housing Dataset, which is a very popular dataset for learning machine learning and doing linear regression. So I'm going to replace all of this. Let's print it out. So this is a complex data set that has a bunch of features, as you can see, the median income, house age, average rooms, average bedrooms, and so on. And the thing that we're trying to predict is the median house value. So all we're doing is importing that data set, putting it into a data frame. We're telling it which column is our target, which is the median house value, and then we're printing out the head of the data set. Now what we're going to do is extract the X matrix in the target variable Y from this data set, from this data frame, and print out X. And here we go. So it's not really easy to look at. It's kind of tricky to look at because it's a very big matrix with many features and many instances inside of it. We can actually see how many there are by doing describe. So there are 20,640 instances in this data set. So we've extracted our variables, and now what we want to do is do a little bit of pre-processing so that we can make this work for us. We learned about pre-processing in my other videos in this series. We're just going to keep this as simple as possible because we're really just trying to focus on gradient descent here. What we want to do is just make it so that this data set, everything is on the same scale. So we learned before about feature scaling. Let me print this out again. So as you can see here, these numbers for these different features all are on different scales. So this one's like 300, this one's just 1, 0.9, 1. So obviously, clearly, these two features are on different scales. And then you have other features, so it gets even more complex. But the great thing is that these are all numbers. So since they're all numbers, we can apply feature scaling to all of them at once. We don't have to do a bunch of crap. So to do that feature scaling, we're going to import the standard scalar from sklearn. We're going to instantiate it. We're going to fit and transform on X. So it's just going to automatically scale all the numbers just automatically for us, which is great. And then print out and then give you the new X with everything transformed inside of it. And then we're going to add a column of ones to the feature matrix for the first column for the bias term that we learned about before. We've already been doing this. The only difference here is that the code is different. This is just another way of doing it versus the add dummy feature function that we've been using before. And then finally, what we're going to do is print it out so we can see what that looks like. And here we go. So you can see if you look very closely here, we have these arrays. It's a multi-dimensional array because it's a matrix, but you can see that everyone has a 1 for the first column, but you can also see that everything is on the same scale now. They're all like smaller numbers around the same range. So that's great. Now I made a copy of the previous notebook before, so we can do this a lot easier because we only need to make a few changes, but I just think, since we want to learn this, I think implementing it from scratch again is pretty helpful. So we're just going to go ahead and do that. So we're going to make a new code cell here. The first thing that we want to do is, just like before, initialize our hyperparameters for our model, for our training rather. So we're going to do alpha is equal to 0.01. That's our learning rate. We're going to do epochs. We're going to set that to 1,000 again. And then we want to initialize our theta to random values, right? So theta is equal to numpy.random.randn. And then now before, we set it to 2 because we need 2 random values, which is the bias term and the feature weight. But now we have a much more complex data set with multiple features. So we need to grab basically how many columns our X has. We can do that by doing x.shape, then 1. So that will give you how many columns there are in our input matrix. And then we can print out theta. And boom, there's our theta. So this is the bias term weight. Then we have all the weights for the features as well. So looking good. All right, so now let's go ahead and implement gradient descent again. So we'll do define gradient descent. We're going to need our x, we're going to need our y, our theta, our alpha, and our epochs. Okay, so we're going to do m is equal to length, y, so that's the number of instances that we have. The errors we're going to initialize to an empty array. Then we're going to do a for loop, so for in a range of epochs, so it loops however many times we specify. So first we want to do same as before, calculate the predictions. So predictions is equal to x dot theta. Now we want to calculate the mean squared error, so calculate MSE, so we'll do error is equal to 1 over m times the sum of the difference in the predictions and the actual, so y, squared. And then we're going to append that error to our errors array, like so. And then now what we want to do is actual gradient descent. So we want to descend down that error curve, right? So we want to calculate the gradient of the cost function. But this time, instead of calculating each of the partial derivatives manually, we're going to use the full vectorized version of this. So this little equation here to get a vector of all of our gradients all together. We'll do gradient is equal to 2 divided by m times, we want the transpose of x, so x dot t, then we want to multiply that times x times theta, the predictions, minus the actual. And let's see if that lines up. So we have the predictions minus the actual times the transpose of x multiplied by 2 over m. Looks good to me. So now this should be a vector with all of our gradients. So for the bias term and the features and all that stuff like that. And so this vector here should be the same shape as our theta, because if the gradient is a vector that has all of the gradients specifically for each of the theta values, it should be the same shape as the actual theta itself, obviously. So theta is equal to, and now we want to do theta minus the alpha times the gradient. So what this is doing is figuring out how each of the different parameters of our model affect how the error changes using a partial derivative, but all combining into one thing. And then what we're doing is modifying those model parameters depending on the gradient for each of the values in the vector. So we're multiplying the alpha times each of those, and that tells us how far to step and how far to change each of those model parameters, including the bias term and the feature weights, okay? So hopefully that makes sense, but as you can see here, it's much more simplified versus what we did before. It's very similar though. So before we had to calculate the partials one by one, or the gradients one by one using the partial, and then we had to modify it one by one. But in this case, we're combining it all together to do it all in one go for no matter how many features we have. So we could have one feature, we could have 20 features, we can have 300 features, however many, and we could still calculate and do gradient descent either way. So that is really cool, and why this implementation is better. So with that said, now we want to return our theta and our error same as before. And then let's go ahead and actually call this. So gradient descent, pass in our x, pass in our y, pass in our theta, alpha, epochs. And here we go, here's our theta with the proper values, hopefully. What I want to do now is try and just get the predictions as a whole with the final theta value. So predictions is equal to x dot theta. So something I wanted to do is just kind of print out the difference between the predictions and the actual values for the first 5 instances in our dataset. So this piece of code here will do that. So it'll just show the actual versus the predicted in a little table for us. As you can see here, they're different, but they're pretty close. So that's a pretty darn good sign, except for this last one here. That one's kind of far off. But like I said before, in the future, we'll learn about the different metrics we can use to actually quantify this in a more just a better way. Here's an example of how you can do that. So you have the mean squared error, you have the root mean squared error, you have the R2 score. So here's what those look like. You just want these to be as low as possible. And then the R2 score, you want to be as high as possible. So that's a decent score, not too good. It really depends on the context of your data set and the model and all that stuff. But for now, though, I want to go ahead and show you how the error changes over time, because I think that's the most important part for learning how gradient descent works. Same as before, we'll just plot our errors array, print out the last one as well. And boom. So look at that. First of all, I want you to notice that the error is a lot smaller. And also you can see that it doesn't exist on a exponential scale. It's literally 6, not 6 times 10 to the 9th power. It's literally just 6 and then 1 and then 0. So as you can see, it starts off around 6 and then quickly descends down to below 1, but not quite 0, and then slowly plateaus closer to 0. So gradient descent is working way better on this dataset for the training of this model, which is great. And I think that has to do with the size of our dataset. So the thing that would make this model better is not changing how our gradient descent works. That's not going to change. It's the same implementation. What's going to matter is tweaking our hyperparameters, but also tweaking our feature selection. So, like choosing which columns actually have better meaning than others. Like some of these aren't even relevant probably. So getting rid of some of these columns might help. Just other stuff that you can do. But generally speaking, though, we have successfully implemented a gradient descent algorithm on that dataset, which is pretty exciting if you ask me. So let's just play with these hyperparameters real quick to see if that changes anything. So we'll set it to a higher number, and then we'll leave the epochs. So let's run that, see what that looks like. And boom, you can see that with a higher learning rate, it descends very rapidly. and then plateaus right away. But if we set a much lower learning rate and then let's say 10,000 epochs, let's see what that looks like. That kind of checks out, right? Because we have a smaller learning rate, so it takes longer for it to descend down this curve here. But eventually, once it gets down to 10,000, it's much more closer to zero. Adding more epochs would help here because it has not quite plateaued yet. Another thing that you can do to tweak your gradient descent algorithm is, we're seeing that with a higher learning rate, the algorithm basically plateaus like right away, and it just sort of stays there for however many epochs we have. What you can do is code your algorithm so that if it determines that the values of the error are not changing very much, the algorithm can just stop itself so that it's not going to continue running for no reason. And yeah, that's pretty much it for this video, everybody. I really hope you enjoyed this video and hope you learned a lot. Gradient descent is one of the first things that you learn in machine learning because it's used with linear regression, but it's also pretty hard to understand as well. So I really hope I was able to explain this in a way that makes sense to you guys. If there's anything that I can do to make it a little bit to understand, please let me know in the comment section below. And if it was understandable to you, please let me know as well. I'd love just any feedback. I really appreciate that. So with that said, that's all I got for this episode. Stay tuned for more videos, and thanks for watching, everybody. So that's it for this video, everybody. I really hope you learned something new. If you liked the video, please hit the like button, and if you want to see more, hit that subscribe button. Make sure to also check the description below for important links to code and other resources, but also really important, join our Discord. We have a big community of over 5,000 programmers, and it's a place where you can find new friends or get help on any code that you're stuck on. If you want to support what I do on this channel, please consider hitting the join button below, and this will allow you to support my channel for as low as $1 a month, but there are different tiers to choose from if you want to. For anyone that becomes a member on my channel, you get a special rank on my Discord server, early access to new videos, and you can just see yourself on the screen right now. So if that sounds cool to you, feel free to join. If you don't want to, that's fine. If you can't, that's okay too. I really just appreciate you watching the video anyway. Thank you so much. And that's it. Peace.